In this video, we're going to go over zeros of a polynomial. We're going to talk about the remainder theorem, the factor theorem, and the rational zero theorem. You might recall in the previous videos that if we had a graph, we could find the zeros of a polynomial. But if we didn't already have a picture of the situation, it might be hard to find the zeros of the polynomial. And today we're going to get the tools to find the zeros if we don't have them already. And these three tools, the remainder theorem, the factor theorem, and the rational zero theorem, are going to help us do that. The remainder theorem is the first thing we're going to go over. If a polynomial is divided by x minus k, then the remainder is equal to f of k. What does that mean? It means that if we're dividing a polynomial by something, then it's the same thing as just plugging it into the function. So this could be a shortcut for determining if a number is in fact a factor of a polynomial. So here we have f of negative 6. And we want to know, say if we want to know if the remainder was 0. If the remainder was 0, it would be a factor. Then we could do that two different ways. We could either do synthetic division with negative 6, or we could plug negative 6 in for each x, and both of them would tell us the remainder of the function. Or both of them could tell us the value of the function. So it works both ways. We can do this problem, find f of negative 6, using synthetic division. If it says to find it using the remainder theorem, then we want to use synthetic division. So instead of plugging negative 6 into this, we can simply do synthetic division. So let me pull out a clean sheet of paper, and I'll do this right below it. So we're going to take our coefficients, 5, negative 4, 3, negative 2, 1, and negative 1. Take the time to double check that you've got all the right numbers and all the right signs, because if you don't, you're not going to have the right answer. Our 5, 4, 3, 2, 1, 0, all the powers are included, so we don't need any zeros. We're going to divide this by negative 6. Remember, that's to check to see if x plus 6 is a factor. Because if we solve x plus 6 equals 0, we get negative 6. So to do this, we drop the 5 down, we multiply negative 30, and we add negative 34. We multiply. 6 times 30 is 180 plus 24. That is 204. We add 3 to get 207. 6 times 7 is 42. 6 times 12, or 2 is 1200. So that's negative 1242. Add the negative 2, negative 1244. Multiply that by 6. 6 times 1200 would be 7200, plus 6 times 4 would be 240. So we're at 7, 4, and another 24, so 64. Positive. Add 7, 4, 6, 5. Multiply that by 6. Let's see, 6 times 5 is 30. 6 times 6 is 36. 6 times 4 is 24. 25 to 6 was 7. 6 6 times 4 is 24. And 6 times 7 is 42 plus 2, 44. 44790. And that's negative. Kind of crowded in here. Thinking about redoing it to make more space. Negative and a negative, so that's going to be negative 44791. Okay. So that's our remainder. And what we would find if we plugged negative 6 into the function, if we would get the same answer. And I did do that on the calculator. I put 5 times negative 6 to the 5th, minus 4 times negative 6 to the 4th, plus 3 times negative 6 to the 3rd, minus 2 times negative 6 squared, plus negative 6, minus 1, and I got the same answer, 44791. And that's what the remainder theorem says. It says you can just plug the number into the function to get the remainder, or if it says to find the value using the remainder theorem, you would actually find the remainder using synthetic division. That can come in handy for finding whether or not the remainder is 0 fairly quickly. The next theorem we're going to go over is the factor theorem. The factor theorem says k is a 0 of f of x if and only if x minus k is a factor. If x minus k is a factor, k is a 0. Okay? Remember when we had quadratics like x minus 2 and x plus 3? Those were factors, and when we had those factors, then the factors produce zeros. And this factor theorem says if x minus 2 is a factor, then x equals 2 is a 0. Or if x plus 3 is a factor, then x equals negative 3 is a 0. So this is maybe a little bit of review, but it just puts it down as an official rule. So the factor theorem says if it's a factor, then that's a 0. Or if this is a 0, then this is a factor. We kind of use this. Have you been using this already? Alright, so show x plus 2 is a factor. So to show it's a factor, we can show that k is a 0. So we could do that two ways. We could find f of negative 2, or we could do synthetic division with negative 2. And if we got that this is 0 or the remainder of 0, then we would show that x plus 2 then we would show that x plus 2 is a factor. So here we have our polynomial. Here. Move all this up here. So we're given, not quite so far up. Okay. So we're given the polynomial x cubed minus 6x squared minus x plus 30. And we want to show that negative 2 is a factor. So we could take f of negative 2. We could do negative 2 cubed minus 6 times negative 2 minus negative 2 plus 30. We would get negative 8 plus 12 plus 2 plus 30. And let's see, this doesn't look like it's going to add up to 0. So I could already show that it is not a factor, unless I've made an error. So we have negative 2 cubed minus 6 times negative 2 squared minus negative 2 plus 30. Now this is going to change things. I need to square that 2. 6 squared, negative 2 squared is a positive 4. Positive 4 times negative 6 is negative 24. Now it looks like it might, because see how these add up to a negative 32 and those add up to a positive 32, and it's 0. So yes, this was a factor. Alright, so we did that. We showed that it's a factor because f of negative 2 is 0, and the remainder theorem said if f of negative 2 is 0, then the remainder is 0. That's what the remainder theorem said. So we showed that x plus 2 is a factor using the remainder theorem. This says to find all the zeros of 3x squared plus x squared minus 20x plus 12 given that x plus 3 is a factor. So we're told that x plus 3 is a factor. So on this one, to do this one, we want to use synthetic division. So I'm going to take my coefficients, 3. I'm going to move my paper up. Here we go. Just fold that other work out of the way. 3, 1, negative 20, and 12. Those are my coefficients. They're all included, 3, 2, 1, 0. And I've got my signs right, 3, 1, negative 20, positive 12. Now, we want to show that x plus 3 is a factor, or we're given that it's a factor. So when we divide this using synthetic division by negative 3, then we should get a remainder of 0. And what's left here will be the remaining polynomial. And because they want all the factors, that's why we need to use synthetic division for this one. Because we need that remaining polynomial to find the other zeros. After we factor out x plus 3, then we'll have a quadratic. And we know how to solve quadratics. So we drop down the 3 and multiply. Negative 9. We add these to get negative 8. We multiply these, positive 24. Add those, 4. Multiply, negative 12. The remainder of 0. If they tell you a factor is a factor and you don't get a remainder of 0, double check that you transferred all the numbers correctly. Double check your work on the inside. Because if it is a factor, it should divide evenly. So this is our remainder. Our constant term, our x term, and our x squared. So we have 3x squared minus 8x plus 4. So that is a factor, and they told us that x plus 3 is a factor for the given polynomial. So what we need to do is factor this part as well. So if we're going to factor that, I'll see if I can factor it this way. If it doesn't factor, I'll have to go back to the quadratic formula. So 3x and x, those have to be used to make 3x squared. Now, I'm putting down my pen and picking up my pencil because I'm not sure about the 4. It could be a 1 and a 4 or a 2 and 8. A 2 and 2. Usually 2 and 2 seems to work more often. This is 6 and here's 2. This looks really promising. If I had them both negative, that would be a negative 6x and a negative 2x, which would give me the negative 8x, and the negative would multiply to the positive 4. I'm picturing what would happen if I FOILed this all out. Would I get back to here? I sure would. So here we have 2 more factors. Now it didn't ask for the other factors. It said find all zeros. So to finish finding the zeros, I need to solve each of these by setting them equal to 0. So 3x minus 2 equals 0, and x minus 2 equals 0. 3x equals 2, or x equals 2/3, and x equals 2. I could do this one as well, but I guess I should. It says find all zeros. It doesn't tell me the 0 from that one, so I'll go ahead and do that one too. X plus 3. I noticed on the homework assignment sometimes they'll ask for this one and sometimes they won't, so read the instructions carefully. So the zeros are -3, 2/3, and 2. That's in order of least to greatest. Those are the zeros of the function. How did we do that again? We took the polynomial and we divided by the known 0. We got a remainder of 0, which gave us a smaller polynomial, a quadratic polynomial. And we know how to solve quadratics. We can either factor or we can use a quadratic formula. Once we have it factored, we get the zeros from those factors and we have our zeros. Okay, that was nice because they gave us the factor. What if we didn't know a factor already? What if we didn't know that -3 was a 0 already? Would we be able to solve the problem? We need another tool to find the zeros. And that tool that we need is the rational zero theorem. The rational zero theorem tells us all possible zeros. If a polynomial has an integer coefficient, and if it doesn't, we can make it an integer coefficient by multiplying, then every rational zero of f of x has the form p over q, where p is the factors of the constant term and q is the factors of the leading coefficient. Okay, so we're going to basically divide the factors of the constant term by the factors of the leading coefficient. So here is another problem, number 4, or example 4, that I've had so far in this video. So we have f of x equals 2x to the 4th minus 5x cubed plus x squared minus 4. I'm noticing there's no x term, so if we want to do synthetic division, we have to make sure we don't forget that 0. Alright, so the factors of the constant term divided by the factors of the leading coefficient. So 4 is our constant term, the leading coefficient is 2. And the factors of 4 are 1. 1 times 4 is 4, 2 times 2 is 4, and 4 times 1 is 4. So 1, 2, and 4 are the factors. But don't forget, to get 4, we can also multiply -4 times -1, and -2 times -2. So we have the positive and negative of each of these are all possible factors of 4. And then we do the same thing with 2. It's only 1 and 2. So positive, -1, and positive or -2. Because positive 1 times positive 2 is 2, and -2 times -2 is 2. So these are the possible factors of 4, and these are the possible factors of 2. This is the possible factors of the constant term. This is the possible factors of the leading coefficient. So what we can do is get several number combinations out of this. We can divide each of the numerators by each of the denominators. So we could have 1 or -1. -1 or 1. We have -1/2 or +1/2. 2 or -2. And notice if I do 2 over 2, I get 1. And negative 2 over positive 2, I get negative 1. All those combinations are already covered, so I don't need to write them again. 4 over 1 or 4 over negative 1. So negative 4 and positive 4 are possibilities. If I take 4 over 2, I get positive 2. If I take negative 4 over 2, I get a negative 2, which I already have those in my list. So for this is all possible zeros for this polynomial. Now that we have the possible zeros, we want to find the actual zeros. But all it says for this problem is to find all possible zeros, and that is done. That's all the possible zeros. So you can write it like this. If you're turning it in by hand, you can write it like this: positive or negative 1, positive or negative 1/2, positive negative 2, positive negative 4. I noticed our online learning system wants it like the top way, so but you can write them like that as well. Now this one says find all the zeros. So I'm going to turn my paper down so I have more space to work. Clean space. Okay, find all the possible zeros of this polynomial. Our polynomial is 4x to the 4th plus 4x cubed minus 12x squared minus x plus 6 equals 0. Find all possible zeros. So we're going to take the factors of the constant term and divide by the factors of the coefficient. So that's 6 over 4. The factors of 6 are 1, 2, 3, and 6. And the factors of 4 are 1, 2, and 4. We have to consider the positive and negative of all of these. So plus or minus. I'll just put that out front. So we have 1 over 1. That's 1. So we have plus or minus 1. Plus or minus 1/2. And plus or minus 1/4. Then we have 2 over 1 plus or minus 2. 2 over 2 we've already covered because 2 over 2 is 1. 2 over 4 we've already covered because 2 over 4 is 1/2. So then we go to 3. 3 over 1. So we got plus or minus 3, plus or minus 3/2, plus or minus 3/4. Then we go to 6. 6 over 1. Plus or minus 6. Plus or minus 6 over 2 is 3. We've already got that covered. And 6 over 4 is 3/2, and we already have that covered. So what we want to do is take this list of possible zeros and find which ones are the real zeros. To find the real zeros, we're going to have to use one of two things. We can plug the numbers into the function and see if we get 0, or we can do synthetic division and see if the remainder is 0. So I'm going to drop that, make a little more room to work here. And this takes time. But once we find 1 or 2, we're really good. So our polynomial again was 4x to the 4th plus 4x cubed minus 25x squared minus x plus 6 equals 0. I kind of prefer synthetic division, but if you have a good calculator where you can just change the x that you're plugging in, just change that one number, or a spreadsheet program, that's really nice because you can just, if you know how to do that. If anybody wants me to post a video on how to do that, then let me know in the comments below. In the meantime, I'm not going to go over that. Let's see. So 4, 3, 2, 1, 0. I've got all my terms here. So if I wanted to check to see if positive 1 was a 0, I could write out my coefficients. Four, negative 25, negative 1, and 6. And then divide by 1 and see if that is a factor. Or actually, I'm checking to see if x minus 1 is a factor. So I drop my 4, multiply, add, multiply, add, 25 minus 8, 17 negative, multiply, it's not looking good, negative 18, multiply 18, not a remainder of 0. So I can rule out positive 1. Positive 1 is not a factor. So I can check negative 1. I want to try the same. That's probably not going to work. You would think you could just change signs throughout, but it does make quite a mess. So 4, negative 25, negative 1, 6. I'm going to see if negative 1 is a factor. I really hope it is, because there's a lot of numbers to go through. 4 times negative 1 is negative 4. That's interesting. And this is 0. So that gives us negative 25, multiplying, positive 25. This isn't going to work. There's no way I'm going to get to negative 6 by the time I get there. I'll show you. 24, negative 24. Nope. It's not a remainder of 0, so this is not a factor. More paper, or maybe there's room for one more down here. Yeah, I like to do the whole numbers. So, and with that odd number in there, would that work very well with the fractions? Should I go to 1/2, or should I skip to 2 or 3? I'll go ahead and do positive 1/2 just to show you it's not too bad. 4, negative 25, negative 1, 6. Although I might tend to do the whole numbers first because it is a little easier. Drop the 4. Half of 4 is 2. 4 plus 2 is 6. Half of 6 is 3. So this is going to turn out even again. That's good. Negative 25 plus 3 would be negative 22. Half of that is, this is looking good actually. Half of that is negative 11. Add that, that's negative 12. And half of that is negative 6. And I add that, it's a remainder of 0. I'm glad I didn't skip the 1/2. Okay, so we have one of our factors. This is a 0. A 0 is 1/2. And so remember that x minus 1/2 is our factor. Okay. So what we have here is actually a smaller polynomial, or do we? This is actually, sometimes you can eliminate zeros by looking at this, but not on this one. Let me show you why. What's left? This is our constant, x squared, x cubed. So we have 4x cubed plus 6x squared minus 22x minus 12. And if we're looking at where that is 0, and we use this rational zero theorem, the solutions to this can be a ratio of the factors of 12 divided by the factors of 4. Well, we already know that the factors of 6 over 4 is going to be our possible zeros, and 12 is going to give us even more factors, But if they didn't work in the previous problem, they won't work in this, so this isn't going to give us any new information. But we do know 1/2 is a factor. We can do a smaller synthetic division now with this new polynomial. So we can start dividing in this one instead of the original one, because we are basically factoring out the x minus 1/2 that we now know is a factor. So we can check and see. By the way, 1/2 could be a factor twice. So if we go through and you can't find another one, then you might have to check +1, -1, and 1/2 again. No, positive -1 will not work, but 1/2 could work again. And that's kind of a tricky thing, is when the same factor works again. But I've seen that in the homework. So if you go through all the rest and none of them work, you might try the one that did work and see if it works again. We can check that right now to see if 1/2 will work again. Remember, that would be that 0 has a multiplicity of 2. 4, half of 4 is 2. 6 plus 2 is 8. Half, I didn't write that right. I was thinking of the 25 we had earlier. We don't have a 25 anymore. Half of 8 is 4. Negative 22 plus 4 is negative 18. Half of 18 is negative 9. That does not add to 0. So this one does not have a multiplicity of 2 of that factor. But it is something to consider that could have a multiplicity of 2. So we keep going. We can do the 1/4. 4, 6, negative 22, negative 12. Let's see if I'm looking back at my list up here that I did in the beginning. That's where I'm getting my ideas from. Oh, I didn't check negative 1/2. I did positive 1/2, but not negative 1/2. I better check that before I move on to the 4th. Be very systematic about it, or you'll leave somebody out. Okay, so now I'm going to try negative 1/2. Negative half of 4. Half of 4 is 2, but make it negative. Add, get 4, negative 2. Add, negative 24. Multiply. Ooh. Half 24 is 12. Negative times negative is positive. Glad I didn't skip that one. So negative 1/2 is a factor. Now we know that positive 1/2 is a 0 and negative 1/2 is a 0. So now we have 2 factors. So here's what we actually have so far. X minus 1/2, x plus 1/2, and this polynomial right here, 4x squared plus 4x minus 24. And this is a quadratic, and we know how to solve quadratics. By the way, this could be written 2x minus 1, and this could be 2x plus 1. Think about that. Pause it if you're having trouble with it. But if you solve 2x plus 1, do you get the answer of 1/2, negative 1/2? And if you solve 2x minus 1, do you get the answer of positive 1/2? So those can be written that way. If you're using an online system and this isn't working, try this. Now we're going to factor this. Oh, I see that a 4 comes out. We'll want to take that out. Front. Let's see. So 4 out here. So I have x squared plus x minus 24 divided by 4. That's 6. There we go. All right. Bringing that 4 out front makes the numbers a little bit easier to work with. Scoot up a little bit. So multiply to 6 and negative 6 and adds to a positive 1. That's got to be 3 and 2. So I set up my parentheses, x and x make x squared, 3 and 2 make 6, and I need it to add to a positive value, so I need a positive 3 and a negative 2. See how that's negative 2x and 3x. Okay, now look, we did it. We found all the zeros. We have 1/2, negative 1/2, 2, and negative 3. So our instructions to find all the zeros, they are, let's see, this is positive 1/2, this one's negative 1/2, 2, and negative 3. So writing those in set notation, lowest to highest. And I don't think our system's going to be too picky about that, but it's a good habit to be orderly. Not that I'm perfect at it, but at math, that's something I'm fairly orderly about. Okay, so there we have the set of numbers, all the zeros for the polynomial. How did we do that? I'm going to recap. What we did is we used the rational zero theorem to find the possible zeros. The possible zeros were a ratio of the last term divided by the factors of the leading coefficient. We wrote all the possible zeros, and then we started working through them to see which ones were zeros. How did we check to see if they were zeros? If the remainder was 0, then that was a 0, which would tell us the factor. Once we had a 0, our polynomial was a little bit smaller. We factored out that 0. So we factored out that 0. We have a smaller polynomial to work with. So then we need to get it down to a quadratic before we were really happy though. So once we did negative 1/2, we got it down to 0. We got it down to a quadratic, and with a quadratic we could factor or use a quadratic formula to find the remaining solutions, to find all the possible zeros right here. Okay, that is how to find zeros using the remainder theorem, the factor theorem, and the rational zero theorem. Let's do one more example. Use the rational root theorem to find the rational zeros. Okay, to find the rational zeros, that means they don't want irrational zeros, the ones that can't be written as a fraction. So basically, I think that what they're saying here is if we have any imaginary numbers, we won't want to include those. Oh, this one, I'm liking this constant term and the leading coefficient. They're small numbers. That's going to be really nice. So P over Q, that's 1 over 2. So the possible zeros, the factors of 1 is positive 1 or negative 1. And the factors of 2 are positive 2 or negative 2. And positive or negative 1. Don't forget 1. Positive 1 or negative 1. So we have plus or minus 1 and plus or minus 1/2. 1 over 2, 1 over negative 2, or 1 over 1, or 1 over negative 1. So we have 4 possibilities. This one is not going to take as long. All right, so we could, we could just do f of negative 1. We can use that remainder theorem. F of negative 1 of 2 times negative 1 cubed plus negative 1 squared minus 4 times negative 1 plus 1. Let's see if we get 0. This is going to be negative 1 times 2 plus 1 plus 4 plus 1. No, that's not 0. Those are all positive. If we do f of 1, 2 times 1 cubed plus 1 squared minus 4 times 1 plus 1. This is 1 cubed is 1 times 2 is 2 plus 1 minus 4 plus 1. 1, 2, 3, 4 minus 4. See, we found f of 1. Our remainder theorem said that if f of 1 is 1, the remainder is 0. So now we know that 1 will work, so we can take our function, our polynomial, 2x cubed plus x minus 4x plus 1, and do synthetic division to see what's left. So here I used the remainder theorem to find the 0, 2, 1, negative 4, 1, but I still need to do synthetic division to get the polynomial that's left. Drop my 2, multiply, add, multiply, add, multiply, add, remainder 0, that's what we expected. Then constant x squared, 2x squared plus 3x minus 1. I'm highly suspicious by the wording of the problem that this doesn't factor. We can try. So 2x and x and 1 and 1. Can we get that to add to a positive 3? If this is, and multiply to a negative 1. I think that's the trick there. There's 1 and 2. If these were both positive, we could get it to add to a 3, but we need to multiply to a negative. So that's not going to work, because I can't get these to multiply to a negative and then add to 3. So if we did the quadratic formula, negative b plus or minus the square root negative b plus or minus the square root of b squared minus 4ac all over 2a negative 3 plus or minus the square root of b squared minus 4ac all over 2a. This is 9 plus 8 is 17. This is going to give us an irrational number, so no additional solutions. So x minus 1 is the only factor, 1 is the only rational 0. Find all rational zeros, 1 is the solution. That is the only solution. There are 2 more zeros, but they are irrational, meaning that if we put this in our calculator, we would have an unending decimal. It cannot be written as a fraction. A single number over a single number. So we only have one rational solution, and that is 1.